Good morning, everyone. This is Professor Coppola broadcasting from the nation's capital, and we're going to be reviewing Chapter 5 and Chapter 6 in preparation for the exam on Friday. And again, let me just check to make sure that we are in fact recording, and we are. Okay, so here is the face page for the PowerPoint notes for Chapter 5. And these are the topics that are going to be covered, that have been covered in Chapter 5. And you should be familiar with each of these points. Okay, let's go to slide 3. Oops. Again. There we go. All right, so slide 3, you need to know the properties of gases. The volumes change greatly with pressure. The volumes change greatly with temperature. Densities of gases are low, okay? Large volume, small mass. Densities are low. Viscosities are low. That is, gases flow easily. Viscosity is resistance to flow. Point 5, gases are completely miscible. That is, they can be mixed together like the air that we're breathing right now, which is a mixture of oxygen, nitrogen, water vapor, carbon dioxide, and maybe some other gases. And point number 6, gases expand to fill the space they are in. Okay, let's move to slide 4. There are two definitions, especially I'd like you to know. Barometers, they measure the pressure of the air or the atmosphere, okay? Manometer, on the other hand, measures the pressure of a gas. Now, I'm just highlighting certain things in the slides, but you should know all the slides. You should know everything on every slide. All right, units of gas pressure. So you should know that 1 atmosphere of pressure is equal to 760 millimeters of mercury, Hg. And millimeters of mercury is shortened to the word torr. So millimeters of mercury is equal to a torr. And again, I told you that torr his name is actually Torricelli, but they shortened it to torr, and they used that to honor him. You should be able to convert atmospheres to millimeters mercury to atmospheres. So if you have atmosphere, essentially you're going to be multiplying by 760 torr. If you're given torr and you want to convert it to atmosphere, you have to divide by 760. And again, using the factor label method, that will help make sure you're on the right track, whether to multiply or divide. STP, standard pressure and temperature. Standard pressure, 1 atmosphere. Standard temperature, 0 Celsius or 273 Kelvin. Remember, when you're working with the equations, you have to use Kelvin. Okay, let's go to slide 8. Okay, Avogadro's law, you should know this. Equal volumes of any gas have the same number of atoms or molecules at the same temperature and pressure. I give you a representation of the law with this diagram with the different balloons. But this was an astounding insight by Avogadro, and it really advanced chemistry enormously, this discovery of his. Okay, 9. So here I show you the equation that represents Avogadro's law. N1 is to N2 as V1 is to V2. And N1, of course, is the number of moles, and V is the volume. Okay, then slide 10 is a problem. I'm not going to go over it now, but you should review that, make sure you understand it, okay? How to use this N1 is to N2 as V1 is to V2. Slide 11, we get to an incredibly important gas law, which is called the ideal gas law. Amazing, holds true for all gases. Pressure times the volume is equal to the number of moles times the constant R times the temperature. Now, R will always be given, and here are this is the value of R that we're using for this equation. There are other values of R with different units, which we'll learn about next semester, but this R is the one we're going to be using, 0.0821 atmosphere liter moles Kelvin. And the nice thing about this constant, it tells you the units, and that means it tells you what the units of all the other variables should be. So pressure has to be atmosphere in this equation. The volume has to be in liters, and it's moles, and T has to be in Kelvin. So if you're given a problem with pressure, volume, number of moles, and temperature, you know it's a PV equals nRT problem, and you may have to convert the units to the proper units. Okay? All right. And then you should review this problem. I'm not going to go over it now. Slide 14. Let's see, slide 14, we get to 3 other gas laws. And what I'd like you to know is the relationship between pressure and volume, temperature and volume, and temperature and pressure. So in Boyle's law, as pressure increases, volume decreases. They're inversely proportional. As temperature increases, volume increases. They're directly proportional. And as the temperature of a gas increases, the pressure of the gas increases. They're directly proportional. And you only have to learn one law, the combined gas law, P1 V1 T2 equals P2 V2 T1. And you can solve any problem involving changing pressures, changing volumes, or changing temperatures. If one of the variables is constant, you just cancel it out. Let's say if temperature was constant, you cancel out temperature, and you just say P1 V1 equals P2 V2. So any gas law problem where there's changing conditions, you just use P1 V1 T2 equals P2 V2 T1. Temperature must be Kelvin to avoid any negatives or any zeros, because you can't really get to 0 in Kelvin. Whereas in Celsius, you can hit it. You can have a 0 and you can have negative, and that'll mess up the equation. Okay. Slide 15. You should look this over and understand it. It's just a picture of the relationships that I just mentioned. Slide 17. Here is a changing gas law problem, and you can look that over. Make sure you understand how to use the equation. P1 V1 T2 equals P2 V2 T1. And there's also a video, which is also can be helpful if you want some more reinforcement. And by the way, I'm always available to help you solve problems. You know, if you're stuck on a calculation, just let me know and we can work it out. I can meet you by Zoom, or you can send it by email. Take a picture of the work that you've done in your notebook and give me the number of the question in Active Chem, and I can help you. 19. Okay, you should know the Dalton's law of partial pressures. Total pressure of a mixture of gases in a system is equal to the sum of the pressures that each individual gas exerts. Okay? So there's an example. So look that over and make sure you understand it. All right, let's go to 22. Oh, one of the greatest theories in chemistry is the kinetic molecular theory. So you should know these points or postulates. The particles of a gas are so small compared with the distances between them that the volume is considered to be negligible, basically almost 0. The particles are in constant motion. The only time, theoretically, where the particles would cease motion is if you got to absolute 0 Kelvin. You can't get to that. So the particles never stop moving. Constant motion. Number 3, you should know that the pressure of a gas exerted is due to the collisions of the particles against the walls of the container. Point 4, the particles are assumed two exert no forces on each other. The average kinetic energy is directly proportional to the temperature. And by the way, let me just go back to my one more thing here I wanted to mention. So let me mention it now. Oops, sorry. Let's take a while here, but we'll get there. One more. Even one more after that. Here we go. This is the one I wanted to tell you. The deviations. Remember, the ideal gas law, PV equals nRT, does not work at high pressures and low temperatures. At high pressures, the molecules are squeezed together, and at low temperatures, they're moving slowly, and they start attracting each other. Normally, that doesn't happen because they're so far apart, and they're moving so fast. They don't have any force on each other. But if you have high pressures and low temperatures, then the ideal gas law no longer works. Okay, just want to emphasize that. All right, go back to slide 23. Okay, so remember, same temperature, same average kinetic energy. Kinetic energy depends on both mass and velocity. So heavier molecules move slower, smaller particles move faster. But if they're at the same temperature, the kinetic energy is the same. The average kinetic energy is the same because kinetic energy depends on mass and velocity. You don't need to know this equation, but it's, if you wanted to calculate kinetic energy, it's mass times the velocity squared divided by 2. But it depends on mass and velocity, okay? And you should also remember larger particles move slower. That should make sense. Smaller particles move faster. So if I gave you an example of two molecules, you just calculate the molar mass. Whichever one has the higher molar mass moves slower. Whatever has the lower molar mass moves faster. How do you get molar mass? You add up the atomic weights. Remember, on the periodic table, the atomic weight is the number below the symbol. And I will give you the periodic table. As always, every exam, you always have a periodic table with for you to look at. Okay? Excuse me. 25. Know the difference between diffusion and infusion. Diffusion, you know. Mixing of gases, gases moving from a high concentration to a low concentration. Diffusion, that funny word you've probably never heard before, just means passage of a gas through a tiny hole, as I show in this picture. And the reason why they came up with this, it's easier to measure the speed of gases by using this technique of diffusion, just letting the gas move through a tiny pinhole. So that's called diffusion. Okay. All right, let's go to slide 27. Okay, Graham's law. You should know this, and it's really not that hard, even though it looks complicated. The rate or speed of a fusion of the lighter gas over the rate of a fusion of the heavier gas is equal to the inverse of the square roots of the molar masses. So over here, you get the molar mass of the heavier one and take the square root of it, divided by the square root of the molar mass of the lighter gas. And that'll tell you how much faster the lighter gas moves than the heavier gas. Okay, so it's really not hard. It's just think about it a little. It should make sense. And let's see, and then in slide 29, I'll give you an example, so you should look that over and make sure you understand it. Okay, slide 31. Oh, there's our stoichiometry problem chart. It just shows that there's another way to get moles. We learned if you have grams, you divide by the molar mass, that'll give you the moles. If you have molecules, you divide by Avogadro's number, that'll give you a number of moles. Now, another way, using PV equals nRT, you can find the number of moles and then proceed with the problem as usual. So on slide 32 and 33, I go through a problem. So you should look that over and make sure you understand it. Slide 34, just a reminder, here's our mole conversion chart. Once we have moles, we can get mass by multiplying by molar mass. But how do we start? How do we find out the number of moles to start with? Well, we use PV equals nRT. So we can use PV, and our N is the number of moles. So it's another way to find the moles. Okay, 35. 35, these are the important equations that you should memorize. Again, they're not that hard. Avogadro's law, N1 is to N2 as V1 is to V2. PV equals nRT. R will be given, and it'll tell you the units that the other variable should be in. And as I say, sing this in the shower. P1 V1 T2 equals P2 V2 T1. Very nice. And if you have a problem with only two of the variables, cancel out the other one and then proceed. And remember, it's the plug and then chug. We plug in the values and solve for the unknown variable. And here's Graham's law again. Think about it, it should be easy to remember that. Just the inverse square roots of the molar masses. All righty. And 36. Again, you should know each of these points from chapter 5. And D2L is posted your learning objectives for chapter 5. And notice the first thing says, learn the major terms and definitions for both chapters. Make a list of them all. So make sure you know what each of those terms mean. I want all of you to get all the matching questions correct. And you also could see other questions as you proceed in the multiple choice. And I also plugged in a couple true and false in the multiple choice. Okay. So those are the points that you should really focus on for chapter 5. However, remember, you should know everything on every slide. I just highlighted some important points. All right. Now what I'm going to do is stop the share, and we're going to go to, so we are recording, nice. And now I'm going to go to chapter 6. Highlight some major things for that chapter. Oops. And the first thing to highlight from chapter 6 is the very bottom. Chemical reactions and phase changes release or absorb heat. And that's why we spent a whole chapter looking at heat. So heat is important in chemistry. And notice as we go through our study of the natural world from the chemical point of view, we're looking at it from all different angles. Chapter 5, we looked at the gases, and eventually we're going to start looking at liquids. But now we want to take a break and look at heat, very important component of chemical reactions. All right. Slide 2, beautiful. Definition of thermochemistry. Thermo comes from the Greek for heat. The study of measuring the amount of heat absorbed or released during a chemical reaction or physical change. And when I say physical change, that means phase changes, melting, boiling, condensing, things like that. Going from a solid to a liquid and a gas, or going back the other way. Slide 3. Oh, beautiful law. I love these laws. Let me just put that away. So you should know the tenets or the points in the law of conservation of energy. And the type of question you got to watch out for is, which of the following is not true about the law of conservation of energy? Or which of the following is true about the law of conservation of energy? So you should know energy cannot be created or destroyed. Energy can be converted from one form to another. For example, chemical energy in a battery produces electrical energy in your computer and in your phone and many other devices. Batteries are awesome. And it took thousands of years for us to discover how to make a battery and then to use it for electrical energy. Pretty amazing. Energy of the universe is constant. And we also call this law of conservation of energy the first law of thermodynamics. It turns out there's 3 laws of thermodynamics, and don't worry, we're eventually going to hit the other 2 laws of thermodynamics. Right now, I just want you to know that the law of conservation of energy, just like the law of conservation of mass, very similar, but the law of conservation of energy is called the first law of thermodynamics. Beautiful. Let's go to slide 4. Let's go to slide 4. Oh, the difference between potential energy and kinetic. It should make sense. Potential energy, that it has the potential. So it has energy due to its position or its composition, and it can be converted to useful work. Kinetic energy is the energy of motion. You push the ball and it starts rolling down the hill. Okay, some definitions. Remember, you should know the definition of energy, the capacity to produce heat or do work. That's our scientific definition. It's not the way we use it in everyday speech. But energy in this chemical sense is the capacity to produce heat or do work. What is heat? Heat we're defining as the transfer of energy from 2 objects due to a temperature difference. Or you could say heat is a transfer of energy from a hotter object to a colder object. It always moves from the hotter object to the colder object. Like you can see in these 2 pictures here. The heat goes from the fire to your hands, or from a hot cup of tea, it goes to the surroundings. Okay. Then we go to slide 7. Oops, slide 7. There we go. So I just want to emphasize that temperature reflects the motion of the particles. The higher the temperature, the faster the particles move. The lower the temperature, the lower the particles move. So as I have here, you increase temperature, particles move faster. Decrease temperature, particles move slower. And if you can't reach it, but if you got to absolute 0, then motion would stop. All right. I talked about here why as temperature increases, you get more collisions. And so in the summer, there's more pressure in your pressure is higher in your tires in the summer. And in the winter, pressure goes down because there's less collisions because the particles are moving slower because it's colder. And you know, today when I checked the pressure on my tires, it said 35. Each tire had a pressure of 35 pounds per square inch. But in the summertime, the pressure of my tires are 40. Each tire is 40 pounds per square inch. Okay, so that should make sense to you. That's why I love the kinetic molecular theory, because it explains observations that we make very, very nicely. Very nice theory, beautiful theory. Love that theory. Okay. Now we get to this idea of state function. Energy as a state function. It depends, it's independent of the pathway. It only depends on the initial state and the final state. Okay. Oops. I guess I want to go to 9, that's why. Okay, there you go. So energy is a state function. A state function is one that depends only on the state of the system. No, not how you got there. And I gave you an example of, oops, what happened there? I didn't want to do that. There we go. I wanted to go to, I think it's slide 11. So you can clearly see that altitude is a state function. The distance is not. It's a path, because the distance this guy took is much less than the distance this guy went. However, they end up at the same altitude. So altitude is a state function. It doesn't matter how you did it. You got to the top, okay? And the reason why we want to emphasize that, because energy is a state function. And so I gave this example. There's different ways you can get to this amount of energy. The amount of energy you have depends on the temperature and the amount of water in this case. So you get 50 grams at 25, and you got to it from two different ways. So the pathway doesn't matter. What matters is the final state. So energy is a state function. Okay. Independent of the path. Then we go to some more terms in our language of chemistry, but it's important. This whole idea of system, surroundings, and the universe. Yeah, here it is. So the system plus the surroundings equals the universe. System is what is the physical or chemical process that we're focusing on. Surroundings includes everything else outside the system. And the system plus surroundings is the universe. And I gave you this picture here. So this is our chemical system that we're talking about, a chemical reaction, a phase change. And then around it is the surroundings. And then the surroundings plus the system gives you the universe. Okay. Slide 16. So some more points to emphasize. So we already said that heat is a transfer of energy from a hotter object to a colder object. We gave it Q because someone else took H, and the enthalpy took H. So it's proportional to temperature. Heat is proportional to temperature, and it's associated with the kinetic energy. Exothermic, remember I gave you a little memory device. Exit, exothermic, exits. So any process, chemical reaction, or phase change that releases heat is exothermic. Remember, we said then that delta H is negative. Any process that absorbs heat is endothermic. And the memory device I gave you was endo enters. Remember, when delta H is positive, excuse me, when it's an endothermic process, delta H is positive. So you should know that. All righty, let's go to slide 17. This is slide 18. Oh, this is the one I wanted. So the basic equation, what's the basic equation? Change in internal energy is Q plus W. Q is the heat, and W is the work, and that nicely reflects the definition. Energy is the capacity to produce heat or do work. So now we put it in equation form. And I also just repeat it there, okay? Q plus W. And then we use that to solve some problems, but let's see, 22. Enter. So remember the signs. First of all, for heat, if Q is negative, that means heat is being lost. It's exothermic. If Q is positive, it means heat is being absorbed. It's endothermic. So going out of the system, we're going to give it a negative sign. Going into the system, we're going to give it a positive sign by convention. So let's see, 24. Again, I'm just highlighting signs. The same thing for work now. And the nice thing about this is that it's parallel. When a system does work on the surroundings, we're going to give it a negative W. In a way you can think about it, work is leaving the system. Think of it that way. So it's parallel to heat leave. When heat leaves the system, it's negative Q. When the surroundings do work on the system, you could think of it like work coming into the system as W. You know, so if you had a gas and then you exerted pressure on it, it would doing work on the system, this W. I just realized that my, I got to do something here. Hold on. Where's my thing? It's not showing me. Let me just stop the share just for a minute. And then I have to go to view. I wanted to go to gallery view. How come it's not showing? Let's see here. I wanted to, let me try this again. Share the screen. Share. I'm going to go like this. Okay, now I know what to do. And show the video panel. There we go. There I am. I appeared again. That lousy Zoom, it took my picture away. There I am again. Okay. All right, so 24. So know the when W is considered negative W and when it's positive W. And then on slide 25 and 26, oops, that's a good stuff. Let's try this. Okay, now do 25. There you go. So in these next two, I'm just going to run. I'm not going to stop it. I'm just going to say, make sure you look this over and understand it. Slide 25 and 26. There will be a question like that. You need to make sure you know the signs of Q and W, and then you just add them together. It's not hard. You have to think. And that's why, by the way, ladies and gentlemen, it's important to get a good night's sleep so you can think clearly, because you need to think. And again, if you understand it, it's easy and you don't have to memorize. The more you understand, the less you have to memorize. The less you understand, the more you have to memorize. So, but think, and you're going to be increasing your brain power, which is good. And you're going to grow in confidence that you can solve problems you've never seen before because you think about it a little bit, draw a picture. Okay, know this definition, enthalpy. Enthalpy, we're going to give the symbol delta H is the heat released or absorbed by a system under constant pressure during a chemical or physical process. All right. Slide 29. As I said, if delta H is negative for a reaction, that's a way of indicating that heat is being lost. So here, 890.3 kilojoules of heat is lost. But over here, delta H is a positive 68. That means it's endothermic, that for this reaction to proceed, it absorbs energy. Okay, so if delta H is positive, endothermic. Delta H is negative, exothermic. Okay. And slide 30, I think, is the next one. There we go. Okay, so the three ways to determine delta H. The first two are by calculation. Data will be posted in tables for the values of delta H, and you can use those in Hess's law, or you can use those given the enthalpy of formation to figure out what the delta H of a reaction is. Seven. So you should look through the Hess law problems that I give them. One is on slide 37. And I'm not going to go through it now, but I just want to say two things. There will be one problem like this on the exam. So you look at the overall reaction you're trying to get to, and you want to find the delta H. You'll be given sub-reactions here. Remember, this is a state function, enthalpy, and it's independent of the pathway. So looking at the state at the sub-reactions, you have to say, well, do I need to reverse the sub-reaction? Do I need to reverse it? And if I do, remember, I changed the sign of delta H. And then, do I need to multiply the sub-reactions by a certain number How do you determine what number to multiply? You look at your overall reaction and look at what you're trying to get. That'll determine whether you need to multiply one of the sub-reactions by something to get the right number of whatever it is in the product. And remember, what you have to multiply everything in the equation by that number, including the delta H. So in Hess's law, you're either going to reverse the direction and then change the sign, or multiply through by something. So look through that problem, and then in 38, whoops, I do another one here, another problem. And not only that, I give you 2 videos with some additional problems where they walk through, both very good. Professor Dave and then Miss Ornstein is very, very good teacher. 5 minutes are short. I always look for videos that are short and good. There's lots and lots of videos on the internet, but I pick the ones that are short and good. And Kendall Ornstein is a very good teacher. Professor Dave has very good graphics, very clear. So if you need some more practice on Hess's law, and you have some in your homework, so if you need help, let me know and I can work with you over the individual problems. Okay, 42. Oops, that is 42. Now 45. Slide 45, I should say. Then we get to this concept of enthalpy of formation. It's defined as the amount of heat lost or gained when 1 mole of a compound is formed from its constituent elements. And remember that little 0 up there means standard temperature and pressure. 1 atmosphere, 273 Kelvin. And then I gave you the example of water. And there's a whole table of compounds, and this is what they mean. It means that to form 1 mole of water, that much energy is released. And that's called the delta H of formation of water. And the reason why you have that 1/2, because you want to do it for just 1 mole. So we had to divide everything by 2. And I showed you this table here. This is the heat released or absorbed. We have a couple where each of these compounds is formed from its constituent element. And it's the formation of 1 mole of each of these. So they standardize it that way, just for 1 mole. Okay. Right. And then we had the problem, I think it's 46. We did that. Next page, notes. Okay, then 49, slide 49. So this equation is really, looks complicated, but it's not. All you do, you'll be given the heats of formation for each product and each reactant. All you do is add up the values for the heats of formation of the products, add up the heats of formation of the reactants, and take the sum of the products minus the sum of the reactants. And remember, you have to take the coefficient in the equation and multiply it by each product and each reactant when you're finding the sums of the products and the sums of the reactants. So even though it looks complicated, it's really not. And this little guy here means sum. It's called sigma. You see it in Excel spreadsheets. And N just means the coefficient. N is the number of moles, but here we're just going to call it the coefficient because they're the same. But it's a coefficient in the equation that you're going to multiply the heat of formation of value for each product and then for each reactant. Okay, let's go to one. So here's a problem that I went through. You should look that over. And actually also, I think on slide 50, slide 50. Okay, here's the first one I did. That's right. So that's one example you can look through. And then on slide 51, there's another example you can look through to help you with that. And then with extra, if you want some extra practice, I have a video here. And it's a long video, but the part where he talks about the heat of formation is at the 6-minute 42-second mark. And he goes through a problem. And of course, you had some in your homework. Okay. The third way to get the heat of a reaction is using calorimetry. And remember, the delta H is the heat of the reaction Q. Delta H is the heat of the reaction Q. And so really, it makes more sense that enthalpy took away the H because we only work with delta H. And when we work with delta H, that's called the heat of the reaction. So the H is heat in that case, even though technically the H is enthalpy and delta H is change in enthalpy. But for all practical purposes, it's the heat of the reaction, Q. All right. So let's go 54. Then we get to calorimetry, and the calorimeter. So you should know the definition is the science of measuring heat based on temperature changes when a body absorbs or gives away energy. And here's our little calorimeter. There's the material being burned. And that's our system. It gives off heat to the surroundings of the water. Temperature changes. And by measuring the temperature change and how much water there is, we can figure out how much heat was given off or absorbed. Okay. Okay. So, concept, very important concept. And as I mentioned in class, I'm not going to ask you the difference between a bomb calorimeter and a coffee cup calorimeter. So don't worry about that. What I want you to know is the key concept. In this particular case, what we did was we put a hot metal into water. And it's a coffee cup calorimeter. The temperature is going to go up. Obviously, if you put a hot metal into water at room temperature, the temperature of the water goes up. The key concept is the heat given off by the hot metal is equal to the heat absorbed by the water. And eventually they're all going to come to the same temperature. So the metal and the water will be at the same temperature. The heat given off by the metal is equal to the heat absorbed by the water. That's the key concept. If you understand that, it'll make life a lot easier. Is that 56? I guess it is. All right, 57. And then we settle something about units. Now, you will be given the two types of units that we use for energy. There are other ones, by the way, but we're just using joules or calories. And the conversion between them, you don't have to memorize. I'll give it to you if needed. 4.184 joules is 1 calorie. And these are two conversion factors. If you needed to go, there's some homework problems you had where you have to convert from joules to calories or calories to joules. And these are your conversion factors to use. Use your factor label method to cancel the proper units and end up with the units that you want to end up with. And then I gave you the definition of calorie. You should know this. It's a scientific definition. It's little c, the amount of heat required to raise a temperature of 1 gram of water 1 degree Celsius. And you don't need to know about the nutritional calorie, okay? We're not going to talk about that, but I did mention that the nutritional calorie is actually a kilocalorie. Okay. Slide 60. Again, that key concept, as I said, the heat given off by the chemical system. In this case, it's the green substance being burned up is equal to the heat absorbed by the surroundings. And then we get to the definition that you need to memorize, but again, it's not hard. It's the mass times the specific heat times the delta T. M is mass. C means constant, which is specific heat constant, is equal to, and delta T is change in temperature. And the nice thing is that the units C will be given because it's a constant. You don't have to memorize constants. And the units of C will be given. And the units will tell you that you've got to multiply it by a mass and by a temperature, a change of temperature. So just by knowing the units of C, that will remind you that the equation is MC delta T, and certain things will cancel out and you end up with joules or calories, depending on the units of C. C can be in either joules or calories. And then the specific heat or specific heat capacity, same thing. It's the energy required to raise the temperature of 1 gram of any substance 1 degree Celsius. Okay, 1 degree. And it can be in joules or it can be in joules per Celsius or joules per Kelvin. And remember, what a calorie is 1 degree of water, 1 degree Celsius. Specific heat is 1 gram of, to raise the temperature of 1 gram of any substance 1 degree. Okay, and but like I say, that will always be given to you. Okay, slide 61. Let's go to slide 62. So you should review this problem as I go through it. Just an MC delta T problem. You just plug in the values and then chug. Just calculate them. And the units will cancel. You'll end up with joules. In 63, I give you another problem. Again, MC delta T. And then if you want more practice, I have a little video here. There's 3 examples of using Q is equal to MC delta T. And then slide 64. This was your last homework problem. And this is your last homework problem in your active chem. And the thing is, again, the key concept was the heat of the metal. You put a hot metal into here. It gives off heat. The ethylene glycol is like water. It's a liquid. It's antifreeze. And the heat given off by the metal is equal to heat absorbed by the ethylene glycol. And so you end up with an MC delta T equals MC delta T. On the right side, it's the MC delta T for the metal. On the left side, it's the MC delta T for the ethylene glycol. They give you the specific heat of the ethylene glycol, and they give you the values of everything except for this guy here, the specific heat of that unknown metal. And so you plug everything in and you solve for the unknown. As I told you, active chem will accept either of these 2 answers because here it's rounded off. And the cool thing about this is then you could identify the metal. This is part of forensic science. You have an unknown metal, and you can do an experiment like this, find out its specific heat, and then look on a table and find out which metal has that specific heat. And you can identify the metal. Okay, now, and I just wanted to point this one out again. And I gave you practice on this in some of your homework problems. So there's your equation, Q equals MC delta T. Now, in a given problems, you'll be given all the variables but one. You could be given a problem where you're given the mass, the specific heat, and the change in temperature, and they ask you to find the heat. Or they could give you a problem where everything else is given but the mass, and they say, okay, find the mass. Same thing for specific heat. Everything else is given. In the equation, find the specific heat. Or find the change in temperature. And then there's one other twist. They could say, I'm going to give you the initial temperature. What's the final temperature? Well, first what you do is you find the delta T. find the delta T. This is given, that's given, that's given. Solve for delta T. Once you know the delta T, the change in temperature, if you know the initial temperature, then you're going to add it or subtract it to the initial temperature, depending on whether the heat is being added or heat is being taken away. Usually it's the heat being added, so that you would add it to the initial temperature. Okay, so ladies and gentlemen, I want you to grow in the skill of learning how to think. You're looking at a new problem you haven't seen before, and you want to think about it. Draw a picture, write down what's given. Very important, write down what's given. Give yourself plenty of room in your scrap paper, and then solve. In this case, it would be solving for the unknown variable. Very good skill. Okay, so these are the equations I'd like you to memorize for the exam. PV equals nRT from the previous chapter. R is given. P1V1T2 equals P2V2T1. Graham's law. And then in this chapter, chapter 6, delta E is equal to Q plus W. Remember, you have to know the sign of the Q and the W. If they're leaving the system, negative. If they're coming into the system, positive. And then here is the heat of enthalpy equation. Although it looks complicated, it's not. And then Q is equal to MC delta T. Again, the value of R will be given, and the specific heat will be provided with, and both provided with their units. The units are very informative to you. Okay, so here are the learning objectives for exam 3. So you should use these to guide your study. Again, know all the terms. Now, I also have one other added feature for chapter 6. I posted another video on D2L, along with the chapter 5 and chapter 6 slides with additional problems. So there's a few additional problems, and I go over each additional problem to give you some extra practice. So just to close here, get a good night's sleep so you can think clearly the next day. There will be 40 matching questions. There'll be 10 matching questions with terms, and then 40 multiple choice. Within the multiple choice, there's a few true and false that are put in there. Very important skill to learn is, if you get stuck, move on. Don't spend 20 minutes on one question. No, it's not good. All the questions are worth 2 points. Do the easy ones first. Come back to the harder ones. I do have a few problems toward the end of the exam. So make sure you do all the easy ones first, and then tackle the problems, which involve calculations. Use your scrap paper, use plenty of room, write down everything that's given, draw a picture, apply the equations. Another thing you can do is when you get the exam in your scrap paper, you can write down, some of the equations that you're going to be using. So then you can refer to them. Okay, well, I wish you good luck. And if you need any additional help, just contact me. We can have an individual Zoom session, and this would be basically for the solving problems from the homework. And I'm also available before and after class, and anytime by email, 24 hours a day, 7 days a week. I'm on call for you. As I say, just send me the question you're working on. Take a picture of the work in your notebook so I can see what you've done, and then I can help you to solve it. Okay. I think I've talked enough. So this is, well, let me give you the big view. This is Professor Coppola signing off from the nation's capital. Have a great rest of the day and good luck on the exam.